What is database sharding? What is it used for? How does it work? And what are the different sharding strategies? What is consistent hashing and what does it have to do with sharding? For all these questions and more, let's dive in. Hello and welcome. My name is Amr Al-Haru. In the previous video, in the Advanced Database Topics playlist, we talked about distributed databases. One of the techniques used in distributed databases that we mentioned was data sharding. This is used to scale and split the data across multiple nodes. Today, we are going to dive into database sharding into more detail. To recap what we talked about in the last video, and I will also link that video in the description and up on the screen. So sharding means that if we have a data set, and we want to store this and process this data on our distributed database. The distributed database has multiple servers or multiple nodes. Then sharding means that we're going to split this data across these nodes such that each node is going to have part of that data or a subset of that data. And those subsets are not overlapping, so each subset is completely distinct from the others. Not only do we split the data, but also this ends up splitting also the query processing. So when we have queries, these queries get distributed among the different nodes. Each node will handle part of those queries. This has several benefits, as we have talked about before. It lets us handle the growth in our data. If we cannot store all the data on one server, this way we can store it on multiple nodes. It also reduces the bottlenecks for queries, since now queries will be processed in parallel. So each of these nodes or each of these servers will be handling part of the query, usually a smaller part rather than handling the whole query. So queries can be much faster. Also, in some cases, for some queries can be directed to a subset of the servers so that the other servers are still free to process other queries. And also it helps us ensure that the system can scale horizontally, because the more data that we add, we can add more servers and more nodes, and this can go on scaling horizontally as much as we like, whereas vertical scaling can be a little bit more difficult and limited. Again, we talked about this in the previous video, so please watch it if you have not seen it already. All right, now let's dive into the architecture of sharding. What does it look like on database system? How does it handle requests and so on? I know in the previous video we talked about distributed databases, and we said that a distributed database is still treated as a single database from the outside perspective. So for a user or for an application that is dealing with this database, to them this is still a single database. Even though it is distributed among multiple servers, it is still seen from the outside as one database. Sharding means that we are splitting the data across multiple nodes, right? In this case, we refer to these nodes as shards. We're not just using them for storage. Like, it's not the case that we're just using the storage aspects of these nodes to store the data and then have a single database, retrieve the data or read and write to these storage, systems. In a sharded database, each node is actually a separate database internally. Again, to the external world, to users and to applications, they appear as a single database, but internally, from the internal implementation point of view, each of them is a separate full-fledged database instance storing part of the data. So let's look at that in a diagram to just explain what we're talking about. In the unsharded database version, the regular version that most people are have dealt with, you have one database. This database stores all the tables that we have, and any application or users deal directly with that database to read and write their data, right? Now, when we go to the sharded database version, like I said, we have multiple database instances running. Each shard runs a database instance. The data is split across these databases, so each table or each data set is split across the shards. Like I said, we call these shards in this case. And now, how do we handle requests, or how do users or applications handle this, since we have multiple databases running in the background, but we need to treat them from a user perspective as a single database? So there is another component, or sometimes they're seen as multiple components that handle this. So we have something called the shard manager, and we have the query router. Sometimes they are referred to as a single component in some of the literature, but sometimes they're also seen as multiple separate components. In here, we're going to talk about them as if they're a single component just for simplicity. So the idea is that any request or any query comes to that query router, and then it will figure out how to route the query or how to distribute the query among the different shards. Each shard, since its own database, will take that query, does its own query processing, return the results back to the query router, which will then combine the results and send them back to the application. Like I said, each shard is a separate database. They're completely autonomous. Each database runs on its own. We can add more shards if needed with their own database instances as well if we want to scale the data. So this is how it works in the background. Now, how do we split the data among the shards, right? So there are a bunch of different sharding strategies. This is very similar to what we talked about in the data partitioning video. So basically for a given table, again, we obviously, like if we have multiple tables, we have to split all of them, or at least some of them. So for any table that we want to split across the shards, the first thing we need to do is choose the sharding key. The sharding key is basically one of the columns in the table, which based on the values in that column for each row, it will decide which shard this row will have to go to. So in the end, some of the rows will go to the first shard, some of the rows will go to the second shard, and so on and so forth, based on the value of that sharding key for each row. Now, once we've defined the sharding key, again, this is similar to partitioning key. Once we've defined the sharding key, we have to figure out what is the sharding method or the strategy that we're using. And generally, we have three different strategies. There is directory-based sharding, there is range-based sharding, and hash-based sharding. So let's talk about each of these and see how they work. First, we have the directory-based sharding. Let's suppose that we have a table here like this companies table. Each company, we have data about the company name, country, region, and so on. For directory-based sharding, basically we maintain a mapping from specific values to shard IDs. So suppose that we have 3 shards, for example. Let's say that the sharding key that we're going to choose here is the country. Usually you choose the sharding key based on the distribution of the data, what queries you have. Usually if you have queries that have filters on a specific column, then this column could be a good candidate as a sharding key. So say that we have queries that target specific countries, we're going to use country as a sharding key. So directory-based sharding will say that, okay, we need to specify a mapping from each value in that column to the shard ID. So you might say that Argentina maps to shard number 0, Canada maps to shard number 1, Austria maps to shard number 2, Brazil maps to 0. You can have multiple values mapped to the same shard, that's fine. So basically you have to provide this mapping, and based on that, each row will be directed to a specific shard. So once we have the data already distributed, now how do we handle queries? So first of all, the mapping that we just specified is maintained by the shard manager, right? So shard manager will say, okay, these are the values in the country column and these are the shard IDs that they map to. So now if we have a query coming in and it happens to have a filter on that sharding key, which is the country in this case, then it will look up the value that we have. Here we have where country equals Brazil. So we look at that mapping and we decide that, okay, Brazil is mapped to shard number 0. So the query router will send that query to only shard number 0. It doesn't need to send any queries to the other shards because it knows that those values do not exist in those other shards. So this is what the query router will do, and it will obviously make the performance better because now the other shards are still free and they can be processing other queries as well. In other cases, of course, like this is not always possible. Like if we have a query that does not have a filter on the sharding key, or if the filter overlaps with multiple shards, then the query might have to be broadcasted, which means sent to all the shards. Of course, that is expensive, so we try to avoid that whenever possible. But in some cases, it might be the only option that we have. What are the advantages and disadvantages of directory-based sharding, right? The first advantage is that this is really easy to implement. You just specify this mapping, and then the query router will map from values to the respective shards. It is easy to add new values. If you have new values being added, you just either you can add new shards or you can map them to existing shards like we've seen in the example, depending on also the business logic that you have and how often you might be querying maybe the same values together. Like let's say if you always query, I don't know, like USA and Canada together, it might make sense to put them in the same shard, whereas other countries might be on different shards if you want to direct these queries to specific shards. So there's many things that you can do, and it's very simple just by specifying that mapping. Like we've seen in the example, the query routing can be efficient for specifically point queries that specify certain values, can be directed to the respective shards based on what these values map to. So these are all the pros of the directory-based sharding. On the other hand, the main disadvantage is that it might lead to either data imbalance or load like query imbalance as well, or both. Data imbalance can happen if certain values appear a lot more than others. For example, in the companies table, right, you might have a lot of companies in the US, whereas some other country may have very, very few companies. So the shard that the US maps to might have a lot of data, whereas a shard that another value maps to might have smaller amount of data. Of course, you can try to mitigate that by maybe mapping a lot of different values to the same shard if you know that these values have just a few rows and so on. So there are ways around it, but of course, as the data changes, like if you add more data or delete data and so on, this imbalance can still happen. This can also happen with queries. If you have many queries that target specific values, again, if most of the queries are about the US versus other countries, then the shard that has the US will get most of the load. This shard will be overloaded with queries, whereas other shards might be idle most of the time. So again, this can happen because of directory-based sharding. Now let's move on to the next strategy, which is range-based sharding. This is also very similar. The difference is that instead of mapping from values to shard IDs, here we're going to map from ranges to shard IDs. So again, consider this example. We have the orders table. Each order has order ID, order date, customer, amount. And let's say we're going to choose the order date as a sharding key. Again, based on our application, suppose that we have lots of queries that filter on this order date, so we're going to choose that as a sharding key. So for range-based sharding, the mapping is going to look like this. Say that, from this date to that date is going to go to shard number 0. From this date to that date is going to go to shard number 1. So the mapping is based on ranges rather than single values. Very similar in terms of query routing and the information that we store. So here, the mapping is also stored by the shard manager. And then when we have a query come in, we look at that query, look at the filter. If you have a filter on the sharding key, then you go look at the mapping, figure out which shards overlap with the query. So in this case, for example, this overlaps only with shard 1. So the query router is going to send the query to shard 1 and let shard 1 answer that query. All the other shards do not overlap, so they don't need to get this query, and they can, avoid having to process this query. Of course, again, if the shard mapping, if many shards overlap with the query, then we might have to send it to all these shards. If you don't have a filter on the sharding key, then you might have to broadcast it to all the shards and so on. Since this is very similar to the directory-based sharding, it shares a lot of the same pros and cons. Again, this is easy to implement. It's very efficient for range queries, as opposed to point queries in this case. Data placement can really map to business logic, again, similar to what we talked about in directory-based sharding. If you know that certain ranges, you treat them in a specific way and you want them to be on the same shard, you can easily do that. So there can be a meaning to how you split the data across multiple shards. And the same problem, it can also still lead to hotspots in terms of certain shards being queried a lot more than others, or also the data can get imbalanced as you insert or update the data and so on. Certain ranges may have a lot more data than other ranges. So this is still something that can happen, and it's something that we can mitigate by doing rebalancing the shards and so on, but we need to know that this is a possibility. The third strategy is hash-based sharding. Many of these strategies, if you remember, these are also very similar to what we talked about in the data partitioning video. So you will find that this may sound familiar. So hash-based sharding, again, after choosing the sharding key, now we apply a hash function on that and then do a modulo the number of shards. So if we choose, customer ID, what we do is that we apply hash function customer ID and then do modulo 3 if we have 3 shards here, and then if the result is 0 or 1 or 2, we go and store that data on the respective shard. The main advantage of this technique is that it usually produces uniformly distributed data. The more data that you have, you will find that you're storing roughly the same amount of data on all the shards. Even as you add new data, update the data, and so on, usually the distribution stays pretty much uniform. This is also easy to scale. You can add new nodes and new shards and so on. The hash function stays the same. All the changes is that instead of doing modulo 3, you're going to do modulo 4 or 5 or 6 and so on. So in concept, the hash, the redistribution or the scaling is easy. Of course, there is a cost, which we'll talk about in a bit. This strategy is the most commonly used one in most database systems that support sharding, just due to the fact that it balances the data pretty well. The disadvantages is that there is no really business meaning to how the data is split. You can't reason about what data is co-located on the same shard because it's just depending on the hash function. So this means that most queries are likely to touch all the shards. So in most cases, you will not be able to redirect or reroute the queries to 1 or 2 shards because most likely you need to read data from all the shards. So everything has a trade-off, right? We talked briefly about redistribution or resharding or moving data from shards to another when we want to, let's say, scale or add new nodes and so on. This is something that obviously we have to consider when we have a sharded database. There are situations where we might need to redistribute the data, like for example, if the data becomes skewed or unbalanced, as we've seen in some of the strategies. One shard becomes too full while the others are not, so we need to move the data around. Or we just need to scale up. The data has grown a lot and we need to add new shards. Or on the opposite, if the data is actually not that much and we want to scale down by removing some of the shards, which can happen because shards are expensive, so you don't want to pay for shards if you're not using them. So in all these situations, we need to redistribute the data, right? This usually involves a lot of data movement between nodes, and we've talked about that in the distributed databases video. Data movement involves network traffic. Network traffic is expensive. So this is an expensive process. Whenever you have to reshard or redistribute the data, this is an expensive process. And of course, each of the sharding strategies that we've talked about requires maybe a slightly different type of work to be done. So for range and direct resharding, you need to redefine the mapping, right? For range sharding, you need to define new ranges and map them differently to the different shards. Whether you're adding or removing shards or you're just redistributing the data, basically you're defining new mappings. And the same thing applies to the directory mapping as well. So first you define that new mapping and then you move the data based on the new mapping. Again, obviously the more data that you're moving, the more expensive the process is. Usually for hash-based sharding, the only instance where we would need to redistribute is when adding or removing shards. Because if the shards are the same, usually we keep having balanced data. So we don't have the problem of unbalanced data, but we might need to add new shards or remove shards, in which case we need to, update the modulo that we're dividing by. We divide by the new number of shards that we have and then redistribute the data accordingly. Since hash-based sharding is the most common, let's focus on that for a bit. Even though we don't need to change the hash function, or we shouldn't change the hash function, there can still be a problem, or there can still be a high cost of redistributing the data. If we look at simple hashing, which is the most common hashing technique that we've seen, this is what we have shown in the example. Basically, simple hashing means that you take the sharding key, you apply a hash function, and then modulo the number of shards. This will give you the shard ID, right? This is what we have seen before. Let's split that or zoom into that a little bit. So again, starting from the sharding key, there are 2 steps, right? The first step is applying the hash function. This will give us a range, will give us a value that lies within a range between a minimum and a maximum. Basically, any hash function has this output range. This output range we refer to usually as the hash space. So basically, if you apply this hash function, it will always give you or map to a value within that hash space. That's the first step. And then the second step is that you take that value and divide it by the number of shards, or do modulo the number of shards, and you get a value from 0 to n minus 1. This is the shard ID that we're moving that row to. Basically, regardless of the number of shards, the hash space is the same. So if we're starting with, let's say these are the shard keys that we have, and this is the hash space that we have based on our hash function, applying the hashing function on each of the keys will map to one point on that line between the minimum and the maximum, right? So now, given the number of shards that we have, suppose that we have 3 shards, then we need to do modulo 3. So each of those values on the hash space, once you do modulo 3, it will give us either 0 or 1 or 2. So this will decide where each item will go on the shards. So we will end up with something like this. Now, this is the initial distribution of the data. Now, what we want to talk about is what happens if we want to redistribute the data, right? So suppose in this scenario, we want to add a new shard. So we have this shard 3. So now we need to redistribute. And when we want to redistribute for hashing, what we said we would do is that the hash space is not going to change. Like the mapping of the keys to the hash space is still the same. What changes is, modulo the number of shards, instead of 3 is going to be modulo 4. So when we do this new operation on the output of the hash function, the keys will map to new shards. So now we need to move these keys from their old location to the new location produced by the new operation that we have here. So what will end up happening is something like this. Each key will get shuffled around to the new ID that we got by doing modulo 4. This is obviously expensive because, like we've seen here, most of the keys have moved. So the amount of network traffic that we incur here is a lot. And if we have a system where we expect to be adding or removing nodes all the time, this will add up to a lot of cost. And this can become a bottleneck, and it's pretty much unacceptable to have a system like that. So in those situations, maybe simple hashing is not the best way to do it. There is a different hashing technique that is used for those cases, and this is called consistent hashing. In consistent hashing, we take that hash space that we just mentioned, the range of values produced by the hash function, and we'll just visualize it. Instead of visualizing it as a line between min and max, we're just going to bend that line and imagine it as a circle. So it's still the same space, still the same range, but we just imagine it as a circle instead of a line. We call this the hashing ring in this case. Just a name. Given that hashing ring, again, given the sharding keys that we have, apply the hash function on those keys, each of them will end up at some point on the ring. Now, in simple hashing, the next step that we did to map those two shards was to do modulo the number of shards, right? So take each of these values in the ring, modulo 3 or modulo 4, and then give us value from 0 to n-1, and we map it to the shard. In consistent hashing, we're not going to do that. In consistent hashing, in order to map these keys to the shards, the first thing we're going to do is actually we're going to hash the shards as well. So you hash the shard ID using the same hashing function and map it to the same, the hash ring that we have here. So by applying the hash function to the shards, each of them is going to end up at some point of the ring. The next step after doing that is that we say, okay, now if we travel clockwise on that ring, and you might be seeing different on the camera, but yeah, if we travel clockwise, starting from each key, basically the goal that we're trying to do is map a key to a shard, right? We're trying to figure out where that key should be located. So starting from a key, travel clockwise in the circle, the first shard that you encounter is the shard where this key should be located. So those two keys the first shard that they encounter going clockwise would be S1, so those two keys should be located on S1. Those 4 keys will be located on S0. Those 2 keys will be located on S2. So this is the way we distribute keys among the different shards using consistent hashing. So in other words, we can say that all of the range covered by this red marker, if any key maps to this range, this key will be located on shard number 1. If any key maps to this green range, it will be located on shard number 0. And by maps, I mean when you apply the hash function to the key. And if any key maps to the yellow range, it will be stored on shard number 2. So as you add more data, you hash the key, you see where it lands on the ring, and it goes to the appropriate shard. Of course, you're not doing this manually. This is happening by the database system or by the sharding manager and the query router, right? Now, the main reason we start talking about this is to handle data distribution, right? Or what happens if we want to redistribute the data among the shards. So let's see what happens then. Suppose that we want to add a new shard, right? So we're adding shard number 3. First thing we do is that we're going to hash that shard and also add it to the ring. So let's say shard 3 goes here. So now what? We need to move some of the data. Which data do we move? Look at the data covered by this blue rectangle. This data used to map to S0, right? But now, according to our rule, it should map to S3 because this is the first shard now that it encounters if going from these keys and going clockwise. So these two keys should now go to S3. So we're going to move those from S0, from shard number 0, to the new shard that we just added. All the other keys on the circle will not move. All the remaining keys in the green range still need to be mapped to S0 because this is the first shard, again, clockwise on the circle. Anything in the yellow range still needs to be on S2. Anything in the red range still needs to be on S1. So the only keys that we needed to move here are those two keys that are before S3. So here the data movement is very minimal. And that's the whole point of the consistent hashing. The same thing applies if we want to do the opposite, if we want to remove a node. So let's say we need to remove shard number 0. So first thing, we remove it from the circle, and then we also need to do some redistribution. So in this case, the keys that are in this yellow rectangle, they used to map to S0, but now since S0 is gone, the first shard that they encounter on the circle clockwise is S2. So these two keys should now be moved to S2. Anything else on the circle will remain the same because, again, they are already where they need to be. So again, data movement here is minimal. So we've seen the main advantage of consistent hashing, which is reducing the data movement when adding or removing nodes, right? So what is the disadvantage? Nothing comes for free. Everything has a cost. Everything has a trade-off. So the disadvantage of consistent hashing is that the distribution of keys is usually not uniform, which is very different from simple hashing. Simple hashing, which we talked about before, most of the time the data is distributed pretty much uniformly across all the shards. But for consistent hashing, it's not. Why is that? Because the placement of the shards on the ring is not always equidistant from each other. You might end up with something like this, where the range between S2 and S1, meaning everything that needs to map to S1, is huge, whereas everything that needs to map to the other shards has like a small segment of that circle. So this means that the hash function usually will distribute keys kind of uniformly on the circle. So this means that you will have more items mapping to S1 than anything mapping to the other shards. So basically S1 will have a lot more data, or is more likely to have data than the other shards in this case. And even if we start with them placed equidistant from each other on the circle, like each one of them has the same segment or the same portion of the circle initially, as you add new nodes or remove nodes, this distribution again will shift and things will become unbalanced. So for consistent hashing, more likely that you're going to have unbalanced data, but you're going to save on the cost of rebalancing or redistribution. For simple hashing, you have balanced data, but whenever you need to redistribute, there's a lot of data movement happening. So again, everything is a trade-off. So whichever one you choose depends on the application and your use case. All right. So generally speaking on sharding, when talking about sharding databases, there are some considerations or some other things that we need to think about. One of those things is indexing, for example. Since we've talked about shards and we said that each shard is a full-fledged database, right? Each one of them is its own database. So each of them can maintain its own indexes. So we can create indexes on each shard separately. This will help with whatever queries need to be processed by this shard. So if you have a sharded database, you need to keep into account that you need to create indexes on each of the shards. Another thing to think about is transaction management. Sharding adds some complexity to transaction management as well. All the stuff that we talked about before in transaction management was about a single server database. So in some cases, some of the transactions that you're dealing with here might be a single shard transactions, especially in the case where all the data that you're touching is on one shard. So like, let's say you have a transaction that reads and writes, but all the data is on a single shard. In this case, all the stuff that we talked about still applies. But in some other cases, you might have cross-shard transactions, so transactions that touches data across multiple shards. In this case, obviously, this gets more complex. If you're trying to use something like two-phase locking, for example, you might need to lock multiple shards or multiple parts of the table. Of course, this adds latency and reduces the throughput of the system. A lot of the systems that support sharding may not enforce this, but may have eventual consistency, something that we've talked about before as well. So they may not have the same guarantees as the asset properties that we've seen in many of the databases, but in that case it helps with the throughput and the latency of the system, but at the same time you don't expect the data to be consistent at any given point in time. Another thing to think about is fault tolerance. Again, we talked about this in the distributed database video. Since we have multiple shards, if one shard is down or inaccessible or has a failure for whatever reason, the other shards are still up and running. Again, each of them is its own database, so they will still be able to answer queries and so on. And if we want to improve that even further, we can always use replication, so that each shard now, instead of having a single copy of the data, it might have multiple copies of the data. We usually refer to it as a replica set in this case. So now if one copy is down, we can still get the same data from other copies, depending on what replication strategy we're using, whether we're using synchronous or asynchronous replication. Again, we talked a little bit more about this in the distributed database video, so feel free to refer to that. So these are some of the things that we have to think about whenever you have a sharded database. This is pretty much what I wanted to talk about today, so let's just recap. Again, today we talked about sharding. Sharding means splitting the data across multiple nodes. We refer to them as shards in this case. This is part of distributed databases. It helps with handling data growth, scaling, and so on. Each shard is a full database, independent database that has part of the data and also handles part of the queries. We have the shard manager and the query router to detect or to figure out how to distribute the queries among the shards and to maintain metadata about the shard information, about the mapping from values or from ranges to shards, and so on. We talked about the different sharding strategies, including directory-based, range-based, and hash-based sharding, and we've seen what are the pros and cons of each. We also talked about the need to redistribute the data sometimes if we have unbalanced data or if we need to add or remove nodes. And we talked about one of the techniques that helps with that, which is consistent hashing, which is used, obviously part of the hash-based sharding. We've seen how this can help and how the mapping is achieved in this case, and of course the downside of that as well. And we've also talked about some considerations to think about when you have a sharded database. That's all for today. I hope this video helped shed some light on sharding and its uses. Please let me know if you have any comments or questions. If you found this video helpful, please hit the like button. If you have not subscribed to the channel yet, please do so. With that, thank you so much for watching, and I will see you in the next video.